Hi, today's session will be the last session for the reinforcement learning. So in today's session, we continue the discussion on the Markov decision process, especially the infinite horizon Markov decision process. And we will discuss two representative algorithms for solving the infinite horizon Markov decision process. And based on the discussions, we will quickly take a look at one of the representative reinforcement learning algorithm called the Q-learning. Alright, so we now focus on the infinite horizon Markov decision process with the stationary rewards and the transition probabilities. So that means none of the rewards and these transition probabilities explicitly depends on the time or the stage t. So from now on, we remove the subscript t, right? T from rewards, transition probabilities, and the value functions, right? So given the policy pi and the state s, initial state s, we may forward this process and compute the expectation of the total rewards over the infinite horizon. So we can introduce such measure as the expected total discounted rewards of the policy pi with the discount factor gamma. So this is the reward of some kind of choosing delta 1 of the pi at the first stage, and this is kind of the reward of choosing the action delta 2 according to the pi and the second stage and so on, right? Okay, and for rewards from the second stage, the discount factors are multiplied, and by doing so, we will see each term represent the present worth of each future reward. So some of these rewards is indeed expected total reward over the infinite horizon on the present value basis. So since the gamma is in between 0 and 1, so this expected total discounted reward is bounded above as far as the absolute value of the reward function. This reward function is bounded, let's say above, let's say m. So this ensures the convergence of this sum. The sum is occurred over the infinite horizon, right? So it is possible to fail to converge. So this ensures the convergence of the sum and hence the existence of the value of this v. Alright, so let's talk about the discount factors. The underlying idea is the future benefit or cost are reduced to compare with the present. Or the $1 today is worth more than $1 tomorrow. So note that such discounting is quite natural whenever the value or value of the reward changes over time. So as illustrated in the slide, the discount factor gamma indeed indicate the present value of the 1 unit of the reward received 1 period in the future. So $1 in the period $1 in the 1 period in the future. So $1 in the future is equivalent to the value of gamma today at the time t. Similarly, $1 in the 2 periods in the future, 1 period and 2 periods in the future, is equivalent to the gamma dollar at the times t plus 1, and that is also equivalent to the value of the gamma squares today, right? In the present value, right? So you can think about these relationships. So the discount factor gamma defines the importance of the future rewards. The value of 0 means only short-term or the immediate rewards are considered. So when the gamma is 0, you just simply disregard the future value, future rewards, right? On the other hand, a value of near 1 puts more importance of the long-term rewards, right? So long-term rewards are almost equivalently important as the short-term rewards. And let us define the optimal value function as V star S, which is the maximum value of the V pi S for all possible pi's, right? And we also say that a policy pi star is the optimal if it maximizes the value for every, initial state S, right? So we'd like to note that for every Markov decision process, there exists at least one optimal policy. Right, so we here assume that the policy pi is stationary, which means for every stage, so we use the same decision rule, delta. So I just specify delta infinite. So because every horizon over the infinite horizon, at every stage, we use the same decision rule, delta. So pi, the policy is equal to delta for the stationary policy. Then, as we show in this slide, the value function V pi S is an expectation of the series of the rewards, right? That which satisfy these simple recursive properties, right? So if you follow this rule, right, this one, so I just separate, I take the first one and then the remaining one and then separate it and then take it out the discount factor from the second term, right? And the second term has the same structure as the first one, right? So we can successfully derive this kind of the recursive equations. So according to these derivations, the value of pi at the state S is equal to the immediate reward, and plus the expected discount, the future value of the pi. So we refer to this system of the equation as the policy evaluation equations. So we know for sure we can get the value of the value function for each state S if the action are chosen according to the policy pi. And we can express this recursive relationship with the matrices or vectors. So V pi is kind of the vectors. V pi is kind of vectors, right? Whose elements is the value of the value of pi for each state. So let's say state space is E1, 2 up to let's say k, right? So the element of the vector V pi is V pi 1, V pi 2, and V pi k. So that is the vector of the V pi. Similarly, R pi is kind of the also vector, whose element corresponds to the each reward for each state. So similarly, the R pi can be, so R1 delta 1, R2 delta 2 up to Rk delta k. So R pi is also a vector, right? And P pi is the kind of the one-step transition matrix, assuming that action is based on the policy pi. So I will construct P pi can be, so 1, 2 up to k, 1, 2 up to k, because we already know the policy, right? So this part, this component corresponds to P1 given the 1 delta 1, and let's say this part corresponds to P, the next stage 2 given the current stage 1, and then delta 1, and so on. So you can construct this one-step transition matrix, right? Then does this, the recursion equations can be written in vectors and matrix notations as follows, right? And what we can do, you just move this part to the left-hand side. So I minus gamma p pi v pi is equal to r pi. And we can show that, you can easily show that this matrix is invertible, right? So by taking the inversion, by taking the inverse of this part, that is the thing. So by calculating this part, you know this one and you know this one. If you know the decision rule, you can find out the value of the pi for every state S. So from this, you can obtain the exact solution of the value of the pi, the v pi for every S. Although it involves some kind of inversion of the matrix I minus gamma times p pi. All right, so the recursion property also holds for the optimal value function v star. We can show that the optimal value function v star satisfies this, Bellman optimality equations. This implies we can get the optimal value from this optimality equations instead, right? We do not consider every possible policies. Okay? This v is same as v, right? So instead of using this one, by using this Bellman optimality equations, you can obtain the optimal value function v star. So that implies we can get the optimal value from this optimality equations, right? Okay? So the optimal v star on the left-hand side, right, is equal to v star on this right-hand side. So furthermore, you can construct the optimal stationary policy from this optimality equations. Okay? So by you just find out the optimal decisions and the collection of the optimal decision, you can construct the optimal decision rule. And if you keep using the same decision rule over the infinite horizons, so that must be optimal stationary policies. All right, so next question is how we can compute the optimal value functions, or how we can find out the optimal policy. So basically, we can derive some kind of the iterative algorithms from the recursive property and the Bellman's optimality equations. All right, so first iterative algorithm to compute the value function is called the value iterations. We again note that the v star on the left-hand side is same as the V star on the right-hand side. So what we try to do so is we initialize the V star with some arbitrary values. Let's say zeros. So the V star, the V0, V at the certain, for every state is equal to 0. Right? And we keep doing the computation presented in this slide. So with the initial value of V, right, you just place the value of V, right, initially 0. So at the initial stage, this term goes away, right? And you can find out the value of V by computing this, right? So you place the V on the right-hand side or equations and then get the updated value of the V, right? And you again use this updated V to the right-hand side to get to plug in the right-hand side and get the another V, right? Another updated V. So you keep doing this until the difference between two successive V values in the iterations become very, very small, right? And we can prove that this iterative update will converge to the optimum value V star. So basically what you can do, you just, with the initial value of V, you plug in the number here, and then by using this one, you get this one. And you again plug in the number, and then you again update the value of V until the difference between two successive V's are very small, right? So you keep doing this, right? And then you eventually converge it to the V star, right? And if we converge to V star, then must satisfy this Bellman's optimality equations. All right, so another iterative algorithm to compute the value function is called the policy iterations. The algorithm alternates between the evaluating a policy. We already talked about how to evaluate the policy. That is called the policy evaluation, right? And the improving the policy. So this algorithm starts with the arbitrary policy pi, right? You just choose any policy pi. And in each iteration, we first evaluate the current policy pi, right? Current policy pi. And you just evaluate through the policy evaluation equations. And you can simply obtain the value of the policy pi by using these equations. And then we try to update the policy by using the values of the pi. You plug in, you use this number, this value, and then using the Bellman optimality equations, you plug the number on this part on the right hand side, and you compute. You compute this part and then find out the maximum, the actions, right, for each state. And if we do this procedure for every state, you eventually have the updated policy, right? So in the policy improvement step, with the values of the pi, it select the policy pi star that is at least as good as the current policy pi. So if you keep doing this, you update the pi star, right? And we can show that the value of pi star is endless greater than or equal to the value of pi. So you just alternating two steps. With the initial the policy pi, you just evaluate the policy evaluation step. You get the value of the pi, and then by using the value of pi, you try to obtain the updated policy. based on these Bellman optimality equations. And with this updated policy pi prime, you just evaluate again, right? You just evaluate this updated policy again, and to get the value of pi, right? In this case, pi prime. And then you plug in this number on the right-hand side on the Bellman optimality equations, and to find out the updated policy in the policy improvement step. So you just keep alternating these two sub-steps until no improving action is possible at any state. Okay? That is the concept of the policy iterations. All right, so far we've discussed the infinite horizon Markov distance process and its algorithms. So when it comes to the Markov distance process, we assume that all the information of the reward and the transient probabilities are given, and we try to focus on finding the optimal policy. On the other hand, in the field of the reinforcement learning, focuses on the problem of the learning from experience when the reward or the transient probabilities are not available. So there are several possible approaches to learn from experience. So one is the model-based reinforcement learning, which means we use the experience to learn the transition probabilities, and then use this model of the transition probability to derive a policy. That is some kind of the approach for the model-based reinforcement learning. Another possible approach is the model-free reinforcement learning. In this case, we use the experience to directly learn the value function through the various algorithms, such as the temporal difference, Q-learning, and so on. So we here discuss a Q-learning algorithm briefly. All right, so before examining the Q-learning algorithm, let us first understand what the Q function is. Right? So Q function is a function for calculating so-called the quality of each state action pair. So for example, let's take a look at the policy evaluation equations. So here is the policy evaluation equations, and if we can define Q pi SA as follows: the state action function Q pi SA is the expected return starting from the state S, taking the action A, and then following the policy pi. Okay? So furthermore, we could say that V pi S indeed equal to Q pi S delta S. Right? So if you select the A as a delta S, V pi S is equal to Q pi S delta S, right? So we again use these relationships, right? So you plug this number here, and this part become Q pi S prime delta S prime, right? So we can derive this recursive equations with the Q functions, Q function and Q functions. All right, the Q function holds the recursive property and the corresponding Bellman optimality equations. So here is the optimality equations, and we let the equation inside this bracket be Q star DSA. So I can write in this way. So V star S is equal to maximum of the Q star SA over all A. Right? So then I can write this. Right? So Q star SA is equal to the immediate reward immediate reward of taking action A for the given state S, and plus the maximum total discounted remaining rewards. So we can write this, right? We can write this, and the optimal value is same as the maximum of this one. So this part can be rewritten as maximum of A prime given that Q star S prime A prime, right? So if we use this relationships, I can update this one, right? And then we can finally derive this recursive property of the Q star as well, right? So this recursive equation will be used as the basis for the Q learning algorithm. Okay, in the previous slide, we just derived the Spellman optimality equation for the Q functions. In the reinforcement learning, when we try to learn the Q star directly from the experience, we cannot utilize these optimality equations. Why? Because this R and P are not known in advance. Thus, instead, we borrow the scheme from the value iteration because we have the Q on both sides, and we can apply the scheme of the value iterations for these optimality equations of the Q function. So basic idea in the Q learning is to incrementally estimate the Q values for each pair of these state and actions based on the feedback that is nothing but the reward from the environment and the agent's Q values functions. Right? Here are the steps of the Q learning. So we first initialize the Q function for every pair of the state and action. And let us start the process with a certain initial state as 0. And let's say let t set to be 0. And then for each stage of t after an action at, for the given state as t is selected according to the certain rule or a certain policy, decision maker or agent decide, you will receive the certain reward. You receive the reward from the environment, and then for the certain state, and then if you choose a certain action, that lead to the next state, right? So once you observe them, all of them, right, you update the Q value, right? So Q value for that state and action is updated by current Q value, and the reward you just received, right? Reward plus the maximum of the Q value from the for the next state as t plus 1 with the learning rate alpha, as like in this slide. This is kind of the scheme for updating Q values. All right, so the learning value, the learning rate, the learning value, this term, right? This term, learned value, this term inside the bracket is a kind of the sample. It's kind of the sample of the right-hand side of this optimality equations. So we know that we only update state action pair that is actually visited, right? We do not update every possible pair of the state and action. We only update state action pair that is actually visited. All right? We also need to understand the concept of the learning rate. The learning rate alpha specifies the how much of the new Q value, right, or newly learned value will override the old one. So if we set alpha to be 0, the agent, if set to alpha 0, this term goes away. So the agent will never learn anything. Just stick to the old informations. On the other hand, if we set alpha to be 1, the newly discovered information is the only important thing to the agent to learn. So according to this update scheme, for each state and action pair with the positive feedback, this is a positive, the corresponding Q value will be increased, right? For pairs with the negative feedback, this is negative, the Q value will be decreases. So that is the basic idea about the Q learning. Right, so in the today's sessions, we learned how to solve the infinite horizon Markov decision process, and they introduced the two algorithms to solve. One is the value iterations, the other one is the policy iterations. After then, we discussed one of the representative reinforcement learning algorithm called the Q learning. Right? So that will be the end of the today's sessions. So thank you.